So for problem set 8, number 1, we've got this 30 kilogram mass hanging at the end of a bar. The distance between the cable and the pivot point is 1/3 the length of the bar. And so we pick this pivot point as the center of torques because then we don't have to worry about the reactive forces here, which we don't know. And you can just say the torque from gravity pulling this down into the board is equal to the torque of the cable pulling it up. And you set those two torques equal to each other. We know torque is the vector cross product between radius and force. But because these are perpendicular, the sine theta drops out and it's just R times F. And so it's simply, if you have 300 newtons pulling down, the torque provided by that is going to require 3 times the force if you're pulling up at 1/3 the radius. So we know this tension must be equal to 900 newtons. Now what if instead of a vertical cable, you have a cable at an angle? This changes one thing. All you really care about is the vertical component of that tension pulling up. And then you have a horizontal component pulling across, pulling into the wall. So two things happen. One, in order to get 900 newtons pulling upward at 30 degrees, you need this tension to be 1 / sine theta times that. And so this has to be 1800 newtons in order to have a vertical component of 900 newtons. Now the other difference is for the first time now we have a horizontal component of force on our system. Now the system is being pulled inwards by that cable as well as up. And so now you must have an outward component of force right here pushing against the bar outward. And you can imagine that happening if you were right here with your hand right there and someone was pulling on this cable to hold this up. You would feel a force on your hand. What's that force going to be? You just have to look at your equilibrium equation in the x direction. The vector sum of the forces in the x direction has to equal mass times acceleration in the x direction equals 0. And so this force pulling this way must be equal to this force pushing out. So the horizontal component of tension plus the reactive force at the pivot must equal 0. And the horizontal component is just tension cosine theta. That is 1800 newtons times the cosine of 30 degrees, which is 0.87, plus the reactive force must equal 0. And that's about 1560 newtons. Okay, the negative sign, right, because if this is pulling inward, this is pushing outward. Then how does it change a problem when we say instead of a massless bar, the mass of this bar is 100 kilograms or has a force of gravity of 1,000 newtons on it? That's going to certainly increase the tension because the increased torque of gravity from pulling down on all these points. But so what we do is we just say all this mass is centered into the center mass, which is square in the middle of this bar. Are you sure I can do that? Can I say this mass is distributed over all points, and I'm just going to say it's just like a point mass right at the center of mass, which in this case, because it's a uniform bar, is the center of the bar. The answer is we can do that. We can take all the mass distributed on a solid body, find the center of mass, and pretend that the mass is all at one point where the center of mass is. The reason we can do that is because the net torque of all these different pieces of mass here being pulled by gravity is just the sum of all the different torques from each mass. And so we write that out as a sum, and recognizing that the radius is perpendicular to the force, we drop the cross product and just take a perpendicular radius, which ultimately we just say is just the radius. And we turn it into an integral, and instead of having mass, we have some little chunk of mass. And we integrate over all those distances in that chunk of mass. And this, by definition, is the mass times the center of mass radius. So center of mass can be thought of as a weighted average of all the distances to all the different points on your body. And so we need to integrate over all the masses, but we can't integrate over mass, we integrate over distance. If we want to express that little bit of mass is the linear density times some little distance, dl. And the linear density is just the total mass divided by the length. We put those in, we pull out the constants, and we integrate over the length of the bar, recognizing that r is the same as length. And so we get r squared over 2, that 2 is important. We evaluate at the two limits, and we end up with mg, that's the force of gravity, on the whole bar, times L divided by 2. And if this bar was shaped differently, like this, the center of mass would be over here, but that integral would wind up yielding the same thing, and that's that you could take all the mass of that bar, and it would behave as if the mass was a point mass at that center of mass. Now the question is, why can't we do this with everything? Why can't we do this, for instance, with the moment of inertia? Why can't we say the moment of inertia of this bar spinning around that point is just all this mass centered at this point? And the reason is because the moment of inertia of a body is dm times r squared. So the integral changes everything. So instead of that, we have the parallel axes theorem, where if this was rotating around this point, we would say, the total moment of inertia of this body is the moment of inertia of it spinning about its center of mass, plus the moment of inertia of that center of mass spinning about the rotation point.